So I'm about to enter one of the clean rooms here on campus at Georgia Tech, and as I explained in the previous video, the clean room gets its name from having very clean filtered air. So I'll have to wear a special suit that lets me enter the clean room without bringing in a bunch of dust or dirt. You might think that the suit is meant to protect me, for example, from getting splashed on from chemicals or getting cut or things like that. But actually the suit is there to protect the clean room from me, from all the dirt and dust and skin cells and vapor in my breath, for example, all the stuff that comes off of me that might damage the clean room or that might damage the tools or the electronics that I'm working with. So the suit's there to protect the clean room from me, not the other way around. So when I need protection from chemicals, for example, I have to put on another suit on top of this. Now, when you're manufacturing a microchip, you're basically making lots and lots of very small circuits. So to work, a circuit has to have conductors that are connected together in a special way. And you may or may not know from your science classes, but a conductor is just a material that conducts electricity very well, like metal, for example. And that's why wires are made out of metal. The circuit can't be just one giant conductor though, or it wouldn't be very useful. So we want to have a way where we can allow electricity to flow in certain places but not in others. Kind of like how you want the inside of your fridge to stay really cold in your house or in your apartment, but you don't necessarily want the rest of your house to be the same temperature as your fridge. You know, it would be really cold. So you want certain regions that behave differently from others. So we want to do the same thing with electricity. So we want electricity to be in certain places but not others. So to keep the electricity from flowing in places we don't want, we need a way of making shapes and patterns of insulator material on the circuit as well. So an insulator, you also might be familiar with from science, is just a material that doesn't conduct electricity very well. So it will prevent electricity from flowing through it, and instead the electricity will be forced to flow in the conductive wires that we connect together so that we can make our circuit do useful things. So we're going to go through how we can pattern and place and arrange different regions that are conductive and other regions that are non-conductive that are made from insulators. So the first step we're going to learn about is one way to put an insulator onto our microchip. There are lots of different ways of making insulators, but this is one very simple way, and it's commonly used in all the microchips that go into the computer that you're using right now to watch this video, for example. So this step is called thermal oxidation. Basically, we take a silicon wafer and put it into a very hot furnace and let it sit there for several hours, typically, while we control the amount of oxygen and nitrogen gas that flows past the wafer. The oxygen will react with the silicon and form a very pure glass layer that can be used as an insulator. So that's where we get the insulating material from. We basically will grow it out of the silicon as a glass. This chemical reaction takes place very slowly at room temperature, but it goes a lot faster at high temperatures. So you'll see that the furnace we're going to use can get to incredibly high temperatures. For example, this one, you'll see it reach about 1,000 degrees Celsius, and it's going to be glowing red hot by the time we're done with it. So this is how we'll make the insulator using thermal oxidation in a tube furnace. So first I need to go grab some wafers from my storage box, and I keep the wafers in a special nitrogen-filled storage box so that when they're sitting there in storage, just sitting there waiting, doing nothing, they aren't exposed to oxygen, because as you just learned, when you expose silicon to oxygen, there's a chemical reaction that takes place and grows glass. So if I keep it in a nitrogen box, then this way it won't grow glass when I'm not using it. So that can be very important, because I don't want glass to be grown in certain places that I'm not expecting it. So keep it in a nitrogen box, and in engineering we call this glass an oxide, which is just a short name for silicon dioxide. And silicon dioxide is basically the glass, the substance that forms when the oxygen reacts with and bonds with the silicon. So here I am loading the wafers into the furnace and closing the door, and the door closes really slowly, so I'm going to speed this part up a lot for you so you don't have to sit there and watch it slowly close. After the doors close, we need to wait a couple hours for the furnace to slowly rise in temperature, because it needs to go from basically about 300-400 Celsius all the way up to 1,000 degrees Celsius for us to do the oxidation. So while we're waiting, I'll go put my stuff away and we'll take a little break. To leave the clean room, I of course have to take the suit off so that the suit can stay clean. Put it in this special garment locker. That way, the suit can sit there and stay clean in nitrogen and not get lots of dust on it when it's not being used. After several hours, you can see that the furnace temperature is at 1,000 degrees Celsius, and you can see it just from looking at it. Look how hot it is. It's glowing hot. It's glowing red, orange, like you might see from molten metal or from lava. So once the reaction's complete and the oxidation is finished, I'll take the wafers out and we'll inspect it and make sure that the glass thickness is the correct thickness, and then prepare the wafers for the next step.